We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India. With more than 450 affiliated colleges in its fold operating across 5 zones of the state, GTU, the International Innovative University, your place to move forward.
Hello dear students, today we are going to study about the energy bands and density of states. As we discussed in our previous lecture, that is of classical free electron theory, where when an electron is in the steady state, that means no external electric field is applied, so electron will continue its random motion inside the material. So the free electron model of metals gives us good insight into the electrical conductivity and electrodynamics of metals, but the model fails to help us with some other questions. For example, the relation of conduction electrons in the metal to the valence electrons of free metals or free atoms, and many transportation properties. So in order to overcome, we will have to analyze the microstructural analysis of the electronic materials. So we will initiate with some assumptions. There may be 2 separate bands, a conduction band for electrons and a valence band for holes. Here in this figure you can identify 4 types of electronic materials. First is the metal, semi-metal, semiconductor and insulator, where the energy band versus Fermi energy level is displayed in this figure. You will have the clear idea of this Fermi energy level in the upcoming lectures. Till now, just you have to focus on the conduction band and valence band. If you are observing metal and semi-metal, there is no energy gap existed. Okay, just there is a minor difference in the positions of conduction and valence band, but as far as you will consider the semiconductor and insulator, there is an existence of energy band gap between valence and conduction band. So again we have a clear idea that valence and conduction bands are separated by some energy called band gap energy, which is symbolically represented as Eg. Okay, the energy of conduction band is represented as Ec, the energy of valence band is represented as Ev, and between semiconductor and insulator we can see a major difference between the energy gap. The higher energy gap is observed in the insulator compared to that of band gap in semiconductor. So the examples of exhibited some energy band gap in the electronic materials are silicon and lead. There may be also multiple bands that have the same energy levels, whereby it is called degeneracy. So instead of the well-known 2 valence and conduction bands in some kind of material, you will also identify or you will also experience the existence of different bands because of the holes inside the valence band exhibited the different mass, but there is no energy gap. The energy of all these bands where you are identifying heavy hole, light hole and split off hole. Okay, so the heavy and light holes are degenerate and the split off hole in the valence band is slightly off the valence band edge, that is the maximum. Here you can see. Okay, so this is the model of multiple band where the electron in the valence band cannot directly jump into the conduction band, and this is the model of the conduction band where the valence and conduction bands are separated by the band gap energy Eg. Here the band gap energy is same, but the difference is there are multiple bands inside the valence structure. The type of band gap in semiconductor is important for the selection of material for many electronic devices including thermoelectric devices, solar cells and lasers. There are two types of band gaps in semiconductor, which are direct and indirect band gap. The energy E of a particle is always associated with a wave vector small k or momentum, which implies that for any transition between bands, both energy and momentum must be conserved. So, in this particular site, we have identified two major types of semiconductors which we are going to study: direct and indirect band gap semiconductors. Number 2, when an electron is traveling from valence to conduction band, the energy and momentum before the traveling and after the traveling must be the same. That means energy and momentum must be conserved. So, moreover, when an electron absorbs enough energy, see, electron cannot directly travel to the conduction band. It has to absorb some amount of energy which is higher than this band gap energy. Until and unless this electron in the valence band has not achieved or absorbed such amount of energy, it is quite difficult for an electron to travel in the conduction band. So that's why here we have mentioned that when an electron absorbs enough energy to exceed the energy gap Eg, the electron can jump from the valence band into the conduction band. The source of the energy could be photons, phonons, or electric field. Either it will have some light energy or have some generation of electron hole pairs quantum mechanically, or we have applied some external electric field. These are the three major sources with which electron can only travel from valence to conduction band. Now we will see the major differences between direct and indirect band gap semiconductors, which is again the most important question in view of your GTU examination. The direct band gap semiconductors such as gallium arsenide, the maximum and minimum of the energy versus momentum relationship occur at the same value of wave vector. So this was in the case of direct band gap semiconductors, because there is no position in the wave vector of an electron, either it is in the valence or conduction band. But when electron will travel in indirect band gap semiconductors, the examples are the well-known silicon and germanium. The maximum and minimum of the energy versus momentum relationship occurs at different wave vectors, and this we will see in this particular figure, where you can observe this is the direct band gap semiconductor. So there is no change in the wave vector of an electron because it is a unidirectional. But this is not unidirectional. First of all, electron will achieve some energy higher than this Eg, travel to this position. It will have to divert its direction to reach in the conduction band. So basically this is the diversion in the direction of the electron. In indirect band gap, I am just explaining this figure. The electron cannot directly jump into the conduction band, but once the electron at the valence band edge, that is EV, absorbs the energy either from these three sources and reaches the energy level of the conduction band edge EC across the energy band EG, it can indirectly jump into the conduction band. So here there is a change in the direction of wave vector. Direct and indirect band gap semiconductors have the major differences in their optical properties. In the upcoming lectures, we are going to see the utilization of these semiconductors in various optoelectronic devices, in which we will observe that by having some interactions of light, that is photon, and the electrons of the conduction band of the semiconductor, the clear identification for selection of either direct or indirect band gap semiconductors. So these energy band diagrams will be helpful. For a sense of time, Direct bandgap semiconductors are more efficient photon emitters and hence they are utilized in semiconductor lasers which are made of direct gap semiconductors such as gallium arsenic. Whereas most electronic devices including thermoelectric devices such as your thermometer, your electric heater, the conduction cooktop, okay, so they are built on indirect semiconductors such as silicon and germanium. So here the two ideas are clear. One is for 3 marks question and one is for 4 marks in your GTU examination. The 3 marks question is like this: discuss the energy band structure in metals, semi-metals, semiconductors and insulators. Number 2, that is for 4 marks: distinguish between direct and indirect bandgap semiconductors with appropriate energy band diagrams. So this was all about your energy band and major classification of semiconductors. Thanks for visiting this lecture.